Okay, so this is the next chapter, solving three-dimensional problems. I'll go over the whole PowerPoint. It will covers the whole chapter, which is quite a few exercises. Work your way through it. Again, any problems, get back to me. Basically, three-dimensional problems are to do with this sort of thing here, which is a cuboid, which is actually a cube, actually. So when we do length, we deal with meters, centimeters, and millimeters. Obviously, kilometers is bigger. The Greek reference is the bigger values, so kilo and mega are Greek reference. Centi and milli are Latin. Milli for anything stands for 1,000. Centi is 100. And you can have decimeter as well, which is 10 centimeter, tenth of a meter. Obviously, when you go up to a square, this is 2 dimensions, and then when you go up to 3 dimensions, obviously there. Now, if you ever do physics or maths at degree level, you'll use maths in 4 and 5, etc. Dimensions. But anyway, so we have a length here, and then here we have an area, here we have a volume. Now the important thing here is each of these has a unit of 1. So this is 1 meter, this is 1 meter squared, this is 1 meter cubed. However, when you use lower units, be careful, because it's not just 100 times bigger, because it's now bigger in 2 dimensions, so 100 times 100. So the area here is 100 times 100 centimeters squared, and 1,000 times 1,000 millimeters squared. And the volume, that's 3. That's just 100 times 100 times 100, or 1,000 times 1,000 times 1,000. So 1,000,000 centimeters cubed, or 1,000,000,000 millimeters cubed. Okay, so just be careful when you've got questions there and it's asking you to convert between meters and centimeters and millimeters and kilometers. Okay, so if we look at these things, what could these be represented? So we got A, B, C. So this is a length times a length times a length, which is a volume. Here we have a length times a length plus a length times a length. So an area plus an area is an area. Here we have a length plus a length, take away a length. So this is just lengths. Here we have a length times a length plus a length times length times length, an area plus a volume, which is nothing. There's no unit there. Okay, so that doesn't make any sense as far as our unit's concerned. Here we have a length times a length squared, which is a length cubed, which is a volume. Here we have a length plus a length, which is a length squared is an area. So bear in mind when you do this dimensional analysis, what you're looking for is if they're added together to be consistently the same thing, whether areas or lengths or volumes, and if they're multiplied together, that if there's one of them it's length, if there's 2 of them it's area, and if there's 3 of them multiplied together it's volume. Okay, so these are the 2 sine rule and cosine rules you used before. Okay, we looked at the area as well. You did questions on that. Basically, if we've got a parallelogram here and I want to find this area, I can split the shape up into 2 triangles, find this triangle and then find this triangle and add them together because they're the same. So in this case, the area is a half times 7 times 4 times sine 80. Okay, the angle there was 80 degrees. This length is obviously 4. Okay, so there's 2 of them, and therefore the total area of the parallelogram is twice this, which is 27.59. These are all rounded to 2 decimal places. Obviously they are longer than that. Okay, and so you should be able to do the first couple of exercises now on the chapter. Okay, so let's have a look at this. We want to use that information now. I want to find the shaded area of this segment. Okay, so we've got a sector here and we've got a triangle. So if I take this triangle here away from this sector, okay, then I can work out this shaded region. So the sector area is just 100 over 360. That's meant to be 100 actually, not 110. I do apologise. So the area of a circle is pi r squared. and we've got 100 degrees of the 360, so that's just the proportion, so that is 10 pi. The area of the triangle, we can use our newfound knowledge of a half AB sine theta, and so A and B are both 6 in this case, so half times 6 squared times sine of 100, which is 17.7, so the shaded area is 10 pi, take away 17.7, which in this case is 13.69 centimeters squared. You would have both, all these are centimeters squared. Okay, so when you deal with three-dimensional problems, you're dealing with spheres or cylinders or cones, or this bit down here is called a frustum. So we'll have a look at a couple of examples of how to work this out, and then you should be able to answer all the questions in the textbook. Any problems, because some of them can be tricky, obviously WeChat me or ding me or whatever. So here we have, this is meant to come up. Okay, here we have the volume of the frustum here. Now we can't work it out immediately, so we have to extend this up to get a cone. So imagine this is looking side on here, and we have our frustum here. Now I extend the cone up. Now if I want if I can find the area, the volume of this cone, and then take the area away from the volume of the big cone, then that will leave me with this area down here, much like I did with here. Work out the area of the sector, take away the triangle, and it gives me the shaded bit. Okay, very often in mathematics we can't directly work out what the areas are, or volumes are, but we can if we take things away. Okay, so we want this height here of x. Now the volume of a cone is a third pi r squared h. R is the radius here. Okay, and so we need to find x first. So x over x plus 5, which is the height of the cone, is the same as 16 over 24, because they're similar shapes. Okay, and so 24x is equal to 16 times x plus 5. 8x is 80, so x is 10. Okay, and so the volume of the whole cone is a third pi times 12 squared, which is the radius at the bottom, times 15, because the height is 15, which is 720 pi. The volume of the small cone is a third pi times 8 squared times 10, which is 213 and a third pi, which gives the volume of the frustum as 506 and 2/3 pi. Notice I've left it in pi there. If it asks you to leave it as a decimal, then leave it as a decimal, whatever rounded places that it is. Okay, you're given the volume and curved surface of a cone and a sphere in your form in your on the front of your exam paper. Same as you're given the volume and surface area of a cylinder, and well, in fact, all of them, I'm not going to repeat it. You're given all of these things here, so you don't even have to remember the sine and cosine rules either. You even got Pythagoras theorem, which is a bit weird. Anyway. Okay, so this is a net for a cone. Now, if you look back here, the curved surface of the cone is pi RL, which is this length here. Okay, so we need to show that the volume of the cone is 36 pi root 5. Okay, so if I look at my cone, this is my H, this is my L, and this is my R. Okay, so if I need to find the volume, again, we look back, the volume is a third pi r squared h, so I need to find r and h. Okay, now all I've got is my cutout of my circle here, so I need to work out this arc length here, because this arc length here forms my circumference at the bottom. Okay, and so the circumference at the bottom is 2 times pi times r, which is this bit here, and the circumference here is 240 over 360, which is my fraction of my 360, times 2 pi r, which is again what would be the circumference of that circle if it was 4. Okay, and so that means r is 6. I'm not going to do any working out there. Both those 2 pi's vanish because they're on the same side, and this is 2/3 of 9. 2/3 of 9 is 6. And so h is 9 squared, take away 6 squared, because that's the radius, square rooted, which is 3 times root 5. Okay, and so therefore my volume is a third pi 3 times root 5 times 6 squared, okay, because it's that's the formula, h times r squared. This 3 and this 1/3 vanish, which gives me 6 squared is 36 root 5 pi, which is what we've got up here as required. Okay, again, any problems, email me.